Hello, my name is Adam. In this video, we are going to learn how to make John Conway's Game of Life in Unity. The Game of Life is a cellular automaton devised by the British mathematician John Horton Conway in 1970. It is a zero-player game, meaning that its evolution is determined by its initial state, requiring no further input. One interacts with the Game of Life by creating an initial configuration and observing how it evolves. It is Turing complete and can simulate a universal constructor or any other Turing machine. If you need help at any point in the tutorial, feel free to join our Discord community where we can offer direct help. There's a link in the description of the video. Please consider subscribing to the channel to support the amount of effort it takes to create a video like this one. It would mean a lot to me and it helps drive the growth of my channel. Thank you. Enjoy the video. Okay, let's create a new project using the Unity Hub. In the top right corner, I can click the new project button. At the very top here, we can choose which version of Unity we want to use, depending on which versions you have installed. I'll be using Unity 2021.3, which is the current long-term support version. However, it doesn't really matter what version you use, so feel free to use whatever you have installed. We're gonna select the 2D template here. We need this because we're going to be using tile maps in the project, and the tile maps will be installed by default in the 2D template. Let's name our project Game of Life or whatever you want to call it, and choose wherever you'd like to save your project, and we can click create. From here, it might take a couple minutes to initialize, so we'll pick it up as soon as it finishes. Okay, once our project is set up, let's go ahead and make a couple changes to our scene here. By default, Unity provides us this sample scene. I'm going to rename this to Game of Life. It doesn't really matter, but call it whatever you'd like. On the left is our hierarchy, which you can expand to see all the game objects that exist in this scene. By default, there should be a camera. I'm just going to make a couple changes to our camera here. So first, I'm going to change the background color. I like mine to be pure black for this particular project, but feel free to customize it. It doesn't really matter. And secondly, I'm going to change the size here. If we change the size, you can see this white outline is changing, and you have to have gizmos turned on to see this. So that's this button in the top right corner here. Toggle visibility of all gizmos. So this white outline is representing the area that the camera can see. If we increase the size, it's going to make that area larger. So for Game of Life, I like to increase the size by quite a bit. That way we can see a larger amount of area, and we can kind of see the simulation happen, because a lot of the simulations, they'll have different gliders and things that go off the screen. So having this be a larger size will give us more area to see with initially. It doesn't really matter though, it is pretty arbitrary, so feel free to set it to whatever. Once we actually implement our game, then we can figure out a size that works best, but it's mostly preference anyway, so. But for now, that's good. The other thing we need to do in our scene is set up a tile map. Our tile maps is where we're going to draw all the cells. So let's right click in our hierarchy, go to 2D object, tile map, and rectangular. You should have the options to create a tile map, assuming you created your project using the 2D template. By creating the project with the 2D template, it's going to install all of the 2D packages for you by default, which includes the tile map stuff. So that actually creates two game objects. It creates a grid, and then as a child of that, we have our tile map. Now, for a Game of Life to work correctly, programmatically speaking, we need two different copies of the state of our game. We need the current state of our game, and then we need the next state of our game. So traditionally, you might write a 2D array. You might create a 2D array to represent the state of your game. And so you would have two 2D arrays. You'd have one 2D array for the current state and another 2D array for the next state. And every iteration, you can update the next state based on the current state. And then that next state becomes your new current state. Now, our tile map effectively is a 2D array, sort of. It's not exactly a 2D array, but it's going to represent essentially our data structure where we're going to store all of our cells, and then each cell will have a tile for it. So I'm just going to duplicate our tile map, and that's going to represent our two different copies of the state of the game. One of these will be used as the current state, and one will be used as the next state. It doesn't really matter what you call them. I would call them one current and the other next, but the thing is we're going to actually swap between which one's the current one and which one's the next one. So naming them current and next actually doesn't make sense, because at some points this one will be the current one, and then at other points it'll be the next. We're going to kind of swap between them each iteration. So it doesn't matter what you call them, but just have two identical tile maps under your grid here. And you can just duplicate that. You can right click and duplicate, or I use Control D to duplicate. And that's all we need to do for our scene setup. The next thing we need to do is create a couple tiles that we will draw on our tile map. And we're going to want a tile to represent an alive state for a cell. And then optionally, we can have a tile represent a dead state for a cell. First, I'm just going to create a square sprite. So I'm going to create a new folder. So I'm going to create and right click in our project panel at the bottom, create a new folder here called sprites. In here, I'm going to right click and go to create 2D sprites. And I'm just going to create a simple square sprite. No changes need to be made to it. We can just leave that how it is. Let's also create a folder for our tiles. Now, there's not really a great way to make a tile through the asset menu here. I mean, there is this, but these are like special types of tiles that we don't want. So what we can do is go to our scene view and click on one of our tile maps. And in the top right corner here is this little button that opens the tile palette window. I know Unity has changed where this button is located depending on the version of Unity. I think in previous versions, you might see it floating down here in the bottom right corner of your scene view. I believe you can also just access it somewhere from window, 2D tile palette. So however you access this, we need to open this tile palette here. And if we simply drag in our square sprite that we create, actually first we need to create a new palette. I'll just simply call this palette and let's create. And I'm going to save this inside our tiles folder here. And I'm going to just drag in that square sprite. This is going to create a new tile asset using that sprite. So once again, I'm going to save this in our tiles folder. I'm just going to call this alive. So this is going to be the tile that represents an alive state of one of our cells. And we can close that now. We're good there. Now, we don't need a dead tile. It's completely optional. And usually I don't use one, but it can be a little bit interesting to see what it looks like for the dead tiles. So I'm just going to literally duplicate this. I'm going to select it and press Control D again. And I'm going to just rename this dead. And maybe I'll change the color to red or something. Doesn't matter. Completely optional, and feel free to customize that to whatever you want. I'm also going to get rid of the colliders on these. We don't need colliders for anything. So we don't even have a collider, a tile map collider on our tile map. So it doesn't really matter, but I'm just going to turn off colliders completely. And that's it. So we have our two tiles here that we'll use to draw ourselves on our tile map. Okay, let's create our first script, and really our only script. Let's go ahead and create a new file for our scripts. There's really only one script we're going to write. I guess there's technically is a second one, but there's not much to it. But first, let's right click here and create C# script. I'm just going to call this our game board. It's going to contain all of the main logic for our game and updating the state of our board here. I'm going to drag this onto our grid game object. It doesn't really matter where you put it, but I'm going to put it there. And let's go ahead and edit the script. You could also just double click the file. All right, so I'm going to delete Unity's boilerplate here and just start fresh. The first thing we need to do is get a few references to those tile maps, as well as maybe define a few settings that we're going to want to customize. So let's create a private reference to a tile map. So we need to import using Unity engine.tilemaps. And now we can reference a tile map here. I'm going to call this one current state, and we'll set up another one for next state. So 2 references to a tile map. We're also going to want a reference to those tiles that we just created. So that alive tile and dead tile. So this will just be tile. We'll call this alive tile. And we'll call this dead tile. There's going to be one other thing we want to reference here, but it's going to be a custom type that we're going to reference. We haven't created that yet. So we'll wait to add that. But then finally, we can have a variable to indicate our update interval. So how quickly it iterates to the next state. So I'm just going to call this our update interval. And maybe by default, I'll set this to 0.05. And this is in seconds, by the way. Now, all of these we need to serialize into our editor here so we can assign the values. So I'm going to go through. I'm going to write serialize field in front of all of these. We add this attribute in front of each of these, and this will make it show up serialized so they can be edited in the editor here. So I'm going to drag in a reference to each of our tile maps. It doesn't matter which one you set to current or next. Just make sure you put a different one for those 2. And then for our live tile, drag that in. Our dead tile, for now, I'm going to leave empty. Because once again, this is a completely optional tile. You don't need it. Leaving it blank is totally valid. So I'm just going to leave it blank for now. And I'll show you what it looks like later once we do add that. All right, cool. So to start our game, we need an initial pattern that we're going to draw onto our tile map. And from there, everything will kick off based on that starting pattern. So let's actually create a new script for that pattern to represent a pattern. Let's right click again, C# script. I'm just going to simply call this pattern. Now, this is not going to be a mono behavior. I actually want to declare this we could just do the simple route and declare it just as a struct. So I'll start out. Let's start out with the simple route, and then we're going to update it to be a little bit more advanced. And I'll explain why. So our pattern is just going to contain an array of cells. So this will just be an array of cells. We want to use vector2 ints. So these are essentially coordinates. Each cell is just indicating the coordinates of the pattern. Offset from some origin, right? So assume the origin is 0, 0. We want to turn on or activate certain cells as the initial pattern. And so these will represent those coordinates. So we're going to declare an array here of vector2 int. We'll name it cells. And let's add system.serializable to this. Now let's go back to our game board and let's add a field for this. Let's call this pattern. Now, assuming you added the fact that that's serializable, if we go to our grid here, we can see our cells here. And we can assign those. Now, we also could have this struct in its current state is kind of pointless. We could have just simply done this, and that's fine too. But once again, I'm not going to keep the struct anyways. Let's change this. Instead, I want to do something different, which is I want to make this a scriptable object. And that's because there's a ton of starting patterns you might have in Game of Life. I mean, there's like a bunch of really cool patterns that exist. And it'd be nice to save each of those patterns as its own asset. That way you can just simply drag in a reference to whichever pattern you want to use. And so that's what a scriptable object essentially is doing, is it's allowing us to create our own custom asset type. So I'm going to change this to be a class. We'll keep it called pattern. I don't know why I deleted all. Let's try that again. We'll just change this to be a class, and we're going to inherit from scriptable object. The other thing we need to do is add a context menu so we can create a asset of this particular type. So we're going to add an attribute above our class called create asset menu. And then in parentheses, we'll provide the menu name. And I'm just going to say game of life / pattern. Okay, so let's take a look at what this does now. If we right click in our project, we can go to create. You'll see there's a folder here, game of life, and then pattern. And now we have our new pattern here. And then we have our cells. So this allows us to create, and we can create a bunch of these, right? We can have 20 different patterns, and then we can just assign a reference to the pattern in our game board. So that's what we're gonna do. I'm gonna actually create a new folder called patterns. And let's create our first pattern that we'll use as our test pattern. It's a really cool pattern. You'll see once we actually implement it. I'll show you a bunch of different patterns, but this will be a good one that kind of is very dynamic and has lots of changes to it. I'm going to call this a pentamino R. So there's a few like basic like shapes that like kind of look like letters. It's similar to like Tetris. In Tetris, you have tetraminos. In here we have pentaminoes. Pentamino, it's pence as in 5. So there's 5 initial cells. And then there's a bunch of them. There's a bunch of different letters like O and P, Q, R, S, T, so on. R is one of the most interesting ones. It's super dynamic and just really interesting. The coordinates for this is going to be 1, 0. Then we'll have 0, 1. Then we'll have 1, 1, 1, 2, and 2, 2. And I'll show you what that looks like once we draw it. Maybe I can Google it real quick. Let me see. Pentamino R. Yeah. So this is what it looks like to start. This is the R pentamino. And this is what it would look like to play it. Can we reset this? I don't know. I don't know how this works. Oh, let's reset it. There we go. So this is what it's going to look like once we actually implement everything. So it's a really cool pattern. It's very dynamic. There's a few gliders here that go off. There's some oscillating stuff. There's some oscillators here. There's a lot of cool, interesting things. For such a simple initial pattern, like 5 cells, and you get this really cool simulation. So that's our pentamino R with our 5 cells. Let's go back to our game board here and let's update this again. Let's reference our pattern. And so now that this is a scriptable object here in the editor, it's just going to allow us to drag in a reference to one of our patterns. So we only have the one at the moment, so we can just select that one. But this is where it's cool because you can predefine a bunch of patterns. In my main project, I have like 100 different patterns that are all just saved as their own asset. And so at any point, I can just drag one in to the editor here and then see what it looks like. So that is the whole reason why we don't want to just use a simple data structure. Instead, turn this into a scriptable object. Okay, let's start by drawing our initial pattern on our board. So now we have all that declared. Let's go ahead and add our start function. This is a function Unity will call automatically the very first frame your game is running. Make sure it is capitalized here, otherwise it won't be called. And I'm also going to add another function called set pattern, and we're going to pass in the pattern we want to set. And I will call that function inStart using the initial. Maybe I'll actually call this initial pattern. I guess it doesn't really matter, but yeah, we'll just pass that in here. So the initial pattern you set in the editor will be what we set here. Now, anytime we update the pattern, we should clear this current state of everything. So I am going to add a new function called clear. And here we can say current state dot clear all tiles, next state dot clear all tiles. We'll probably do a couple more things in here as well, but that's the first thing I'm going to do is if you update the pattern, we're going to clear the entire state of everything and start fresh. Okay, so now from here, we're going to loop through all the cells in our pattern. So we can say for int I equals 0, I is less than pattern.cells.length, I++. And what we're going to want to do is update our tile map. So our end goal is to say current state dot set tile, and we need to provide a position. Now notice these are a vector 3 ints, whereas our pattern uses a vector 2 ints. So it's a little annoying, but that's okay. We can say new vector, or actually we can just cast. So here, let me do this. Let's take our vector 2 int, our cell. So let's get our current cell in our array, pattern.cells I, and we can cast this cell to a vector 3 ints. And then we need to provide the tile that we're going to render at that at those coordinates. And so initially these are all the alive tiles. That's the whole point of a pattern, is you're defining what are the initial set of alive coordinates. So we're set that to our current state and we're good there. Now, one thing I would like to do is center this, center the pattern at the kind of origin of our tile map. There are some patterns that are really large and complex, and defining the coordinates for them gets a little crazy. So just to make it easier to sort of center everything, we can offset this position by some centering. But to do that, we need to calculate what the center of our pattern is, and then we can offset it to that. So let's go to our pattern script here, and let's create a function in here that's going to return a vector 2 int. We'll say get center. Now, initially, we can do a little bit of a guard statement here to say if our cells is null or our cells dot length is 0, well, our center is just going to be 0. Assuming we actually have some cells to work with, let's go ahead and figure out what our center is. Essentially, what we're going to do is get the bounds of all of our cells, and then we'll get the center of that. So to get our bounds, we need to store the min and the max. And so initially, both of these will be 0. And then we'll loop through all of our cells. And then from here, we're just going to compare the current min to each cell. So let's just store our current cell, cells I. And so min.x is going to equal mathf.min of cell.x, min.x. So we're comparing, so this is a function you need to provide so that it's just going to return the smaller of the two values. We're taking our current cell with our current min, and it's going to essentially update to be the lower of the two. And we're going to do this same thing for the y-axis. And then we're going to do the same thing for max, but instead, instead we're going to change this to be a max function. All right, so that's establishing the bounds for our for all of our cells. So it's going to find the minimum point and the maximum point. So that's sort of defining the extent of our cells. And then from there, we can interpolate between the min and max to get the center point. And in this case, since there's only 2 points, we can just add them together. Min, I can't type, min plus max divided by 2. If you had a bunch of different points, you might need to interpolate between them in a different way, but this suffices. We just keep it simple and add them together, divide by 2. That's going to give us our center point. We just double check this. So we have min x, min y, cell x, min x, cell x, min x, min y, cell y, min y, max, x, 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 y, 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 max, max. Yeah, okay, everything's good. All right, so that's our center. So here, let's get that center. Okay. So we're just going to call that function on our pattern. So we have our center point. And now we can just subtract this here. So we can say, oh, I don't know why I said pattern, minus center. So we take our current cell, we're going to offset that based on the center point, and then we're good to go. This is just going to ensure that whatever pattern we establish, even for some of the really complex patterns, it'll always be centered at the origin of our tile map, which is just in the dead center of our screen. You don't have to do this. Maybe you don't want to do this, but I prefer to kind of always keep it centered as our starting point. All right, that's actually it. We can at least test this out now. We play our game, make sure we have our pattern set. And there we go. We can see our pentagonal R. It kind of looks like the letter R. And this is where earlier we changed the size of our camera. So this is where mine's set to 30, but maybe you want to be a little bit closer. Eventually these patterns, they're going to once you simulate them, they can start to cover a really large area. So that's where zooming out here helps to see more. But it's just preference, so feel free to change that. All right, now let's start setting up our simulation. So let's go ahead and open up our game board again. And we want to set up a simulation kind of update loop. Now, since we are defining our own kind of custom update interval, we can't really use the main update function that Unity provides. Well, we could, but I personally prefer to just use a coroutine, and then we can suspend the execution of that coroutine based on this interval here. So let's go ahead and do that. First, we need to import using system.collections. And now we can write our coroutine function. So this is going to be a function that returns IEnumerator. I'm going to call this simulates. And I'll explain what a coroutine does in a minute. But let's start our simulation whenever our script becomes enabled. So Unity provides, or will call this function automatically for us on enable. Make sure the casing is exactly like this, or Unity won't call it. And on enable, we will start our coroutine. Okay, in our coroutine itself, we want to continue the simulation while our script is enabled. And so this is where on enable, we start the simulation. And if you then disable the script, our coroutine will stop because our while loop will no longer be true. So our update here will stop. And then the next time you enable the script again, it'll start the simulation again. So this just essentially allows us to play and pause it. Now in a coroutine, you need to yield somewhere in the function. So the point of a coroutine is you can suspend the execution of the function for, let's say X amount of seconds. There are different ways you can yield, but in our case, we want to yield based on this interval. So for example, what that would look like is to say yield return new wait 4 seconds, and then the amount of seconds is going to be our update interval. That's the basic idea. And then of course we should actually update our state. So this will be a placeholder. We're going to fill this out later, but let's add a function called update state. And we want to call this function inside there. So what this does is while our script is enabled, we will update the state of our simulation, and then we'll wait. And then we'll update our state, and then we'll wait. And then we'll update our state, and then we'll wait. So it'll just continue to go on so long as your script is enabled. So let's say our interval is set to 1 second. It's going to update our state. Then it's going to wait a second. And it'll update our state again. And it'll wait a second, and so on. That's the basic idea. Now, there's a couple of things I want to comment on about this. This statement here produces garbage because wait for seconds is a class, so you're allocating memory on the heap. So this is going to create garbage every single iteration, which is not good. Garbage is really bad. It can cause major performance problems. Now, in our case here, this is such a simple project, it doesn't really matter. But it would, in theory, be better to cache this so we don't have to allocate that memory every single time. So we can simply cache it here locally and just say interval equals new wait for seconds, update interval. And And now we can just say yield return interval. So that's one way we can just kind of cache it locally. So it will produce the garbage, kind of produces the memory or allocates the memory on the heap initially once, but then every time we loop, it doesn't need to do it again. That's like a simple way to cache this. There are better ways, but that's a simple way. The only downside to this is if we were to change this interval while our simulation is running, it's not going to do anything because our interval has already been cached at that point. And so changing this won't have any effect whatsoever. And so that could be a downside, right? So that's the trade-off is, you know, you can optimize your kind of memory allocation, but at the downside that you're not able to change this value dynamically. Just for the sake of testing our game of life here, I'm just going to not cache this, even though normally speaking, I would not write this line of code in a real project of mine. Doesn't really matter. It's probably not something you need to be concerned about right now anyways, but it's at least worth noting about this. And once again, there are better ways to cache stuff like this, where you can still have the best of both worlds. There are ways you can cache this where you can use a cache, but still be able to provide different values. And in most of my projects, I have a class dedicated to caching yield statements. I can do stuff like that, but this is just supposed to be a simple tutorial, so I'm not going to bother with any of that. I'm just going to do it the bad way and just produce garbage every single time. But once again, it doesn't really matter. Not for this project, it won't. All right, so we're almost ready to implement the logic for Game of Life. However, there's a few major considerations we have to make first. So one of the challenging parts about implementing Game of Life is from a data structures perspective. Ideally, Game of Life is an infinite simulation, or it uses an infinite grid. So in other words, you can store the position, you can store the state of a cell no matter what its coordinates are. It doesn't matter if those coordinates are in the millions or in the tens. You can store that cell state. Now, our tile map is ultimately what's storing the state of our cells. So the Unity's tile map is implementing that for us. But there are still some issues because we need to know which cells to update, right? The tile map does provide a size. So we can get the overall grid size of our tile map and know exactly what the bounds are, you know, of all the tiles that are being rendered currently on our board, how much area does that cover? And then in theory, what you would do is loop over every cell in that grid, and then you could update its state accordingly. However, this becomes a major problem as your simulation goes on over time, because there are a lot of patterns that create these very complex simulations where there are certain objects that traverse really far, like gliders will just continue to go on forever. And so that the bounds of all your cells becomes larger and larger and larger and larger. And so if you're just looping over every cell in the grid, well, every single iteration of your simulation, you're going to have to loop over even more things and even more things and even more things. It becomes a lot to compute. My first implementation of Game of Life using an infinite grid, I was essentially doing that where I kept track of the overall bounds of the board based on what cells were alive, and it would loop through every position in that grid. And I was able to make some optimizations around this to make sure my bounds was as constrained as possible. However, even then, my frame rate would tank really heavily after running the simulation for, let's say, a minute. You know, at the start of the simulation, I might be running at 1,000 frames per second. And after a minute, I was running at like 10 frames a second. It was really bad. So that's a problem. And that's because with a lot of data structure, well, one of the issues that comes from that is even if you have a dynamically sized data structure, over time, those data structures are going to have to allocate tons and tons of memory to be able to consume the overall size of your grid. So we need a kind of a different way to handle this. many years ago when I first implemented Game of Life, I just had a fixed size grid. It was just, okay, it's a 512 by 512. That's the space we're going to do our simulation in. If there's ever a cell that goes beyond that grid bounds, we just, essentially it just disappears at that point. And that works well. And then you can kind of optimize around, you can optimize that grid size based on your application. You can figure out what size works well, that runs well, and is large enough to handle a big enough space that you can kind of explore some more complex simulations. However, that's not as fun. Like ideally it should be infinite, right? So let me show you what I eventually came up with. It's not the best. There are better algorithms, but they're way more complicated. I want to try to keep this fairly simple. So first let's import using system.collections.generic, and we're going to declare a hash set. And this is going to be a hash set of vector3 int. And that's because our tile map uses vector3 int coordinates. I'm going to call this alive cells. So the problem with using a grid, whether it's a fixed size grid or a dynamically sized grid, is looping over every single cell in that grid. Most of those cells, nothing's going to happen. They're just pointless cells that nothing's going to happen. So one kind of optimization we can make is only keep track of the cells that are currently alive, because we only need to update the state of those cells and the adjacent ones to the alive ones. It is only possible for either the currently alive cells to change state or the cells surrounding that to change state. Nothing else matters. So this will allow us to drastically reduce the amount of cells that we need to check to see if the state is going to be updated. In fact, we will actually declare a second hash set, which is going to, we'll call this cells to check. So every time we update our state, the first thing we're going to do is populate our cells to check with all of the cells that we need to determine if their state is going to change. So that will include all of the alive cells, as well as all the adjacent ones that I mentioned. Now, the reason we're using a set here is because as we determine all of those cells, there are going to be a lot of overlap between them. And the point of a set is that there are no duplicate cells. It will always be a unique set of values. And this is important because as we figure out what all these cells to check are, we don't want to add the same cell multiple times, because then it's just a bunch of pointless. It's just extra things we have to process when nothing's going to change from processing this same cell multiple times. So that's why we're using a hash set here. All right, so first let's update our alive cells. Well, actually, first we need to instantiate these. Let's add our awake function. This is another function Unity calls automatically. Make sure it's capitalized or it won't get called. And in here we can just say new. Same thing for the other one. So we're just instantiating both of those. We could optimize this with an initial capacity, but it doesn't really matter. All right. And then let's assign our initial set of alive cells. So when we set our pattern, we can just add the cell to our, hash set. Now this is expecting a vector3 int, where this is a vector2 int. We could do the exact same thing here and just cast it. However, I don't like the fact that we're casting it twice to the same thing. So I'm just going to change the initial declaration to be a vector3 int, and I will cast this. So I'm going to wrap that whole thing in parentheses. Oops, vector3 int, and we'll cast that. And now we don't need to cast it twice for no reason. Cool. So we're adding our initial cells to our hash set. And the first thing we're going to do in our update state is we're going to add all the cells that we need to update to our other hash set. So first, let's loop through all of the cells in our alive cells. And we for sure will be adding this cell, but we also need to add all the adjacent ones. Let me pull up a notepad here. So let's say that this is our current cell. We have all the adjacent ones. So we have, we've got one to the left, one to the right. We've got, one above it. We've got one below it. We've got the ones at the diagonal. All right, so we need to be able to update. We need to add all 9 of these to our cells to check. And this is where, once again, if we have multiple alive cells, there are cases we're going to be, in most cases, a lot of them are going to be right next to each other, in which case they're going to have a lot of overlap. And so that's why we're using hash set, because we don't want to add the same cell multiple times. But the way you can think about this is -1 to the left. This is +1. Like, so in terms of like coordinates, it's -1, +1, and same thing in the opposite axis. So what we can do is just set up a for loop for int x equals -1. X is less than or equal to +1, x ++. So make sure this is inclusive. Do the exact same thing in our other axis. Y equals -1, y is less than or equal to +1, y++. And now we can get our new cell position. We should do this. Cells to check dot add our base cell position plus some offset here. And the offset is our XY. And the Z coordinate. You don't actually have to provide a Z coordinate, but set that to 0 if you do. All right, so this is just essentially saying, okay, we want to, iterate through all of these. We're essentially setting up a 3x3 matrix, kind of looping over a 3x3 matrix where we have our center tile, and then to the left is going to be -1, to the right is going to be +1, right? And then same thing in the other axis. So this will just kind of quickly add all of our cells to our array. We could manually do this, right? So we can unroll this whole loop and just say, add one cell, add another one, so on. Like, we could just manually add all 9, but this is just a little bit of a quicker, maybe more readable way to do that. Maybe less readable, because it's subjective, but. So anyways, that's the first thing we want to do. And then from here, now we can actually start to process our cells, and only the absolutely necessary cells. We don't need to loop over an entire grid and check hundreds of thousands of cells. We just need to check, a limited amount, the absolute minimum amount we need. With our initial pattern, there's 5 cells, right? And so if we're adding 9, if we're adding all the adjacent ones, at the absolute most, there can be 5 times 9, which is 45. However, once again, there's going to be a lot of overlap. So it's going to be, something less than or equal to that, which is pretty nice. And obviously that will still grow over time. So this will expand over time, and there will be more and more cells. But our population with a grid, as soon as your grid's like 100 by 100, you're doing hundreds of thousands of loops. Whereas if you have 1,000 cells, like, it's still only, there's a big difference. There's magnitudes of a difference if you're looping over an entire grid versus just the individual cells you need. So even though this still expands over time, it's going to be far less than if you were to use some type of grid structure. Okay, finally, we won't add the actual logic yet, but I just want to set up the loop here, which is to loop over now all of these cells to check. And then this is where we'll do all the actual logic for the game. One thing I forgot to do, though, is we need to clear out our cells to check every time we update this state. Before we go and add all these cells to our sets, we want to clear it first. Okay, so we're on to really the last part of our game, and then we can just test it out. So the actual logic for Game of Life is we need to count how many, for every cell, we need to count how many of that cell's neighbors are alive. And then depending on how many of its neighbors are alive, that's going to determine the new state of that cell. So if it's underpopulated, if the cell is currently alive, but it's underpopulated, there's not very many neighbors, then that cell dies. Or if it's overpopulated, it also dies. So if it's underpopulated or overpopulated, that cell will die. If the cell is not currently alive and there are exactly 3 neighbors, so it has the right amount of population surrounding it, then it becomes alive. That's really the rules of Game of Life. That's it. So how do we translate that into code? Well, first we need to count how many neighbors are alive. So let's write a function just to handle that. We'll call this count neighbors. We're going to pass in the cell that we want to check, and it's going to count the amount of neighbors around it. Initially, our count we'll start at 0 and we'll return our count at the end. And this is where we can kind of use this exact same concept here. We can just loop over all of these kind of offsets. We kind of loop over that 3x3 matrix that gives us an offset position in each case. So we can store this vector3 int neighbor equals cell plus some offset. And then we can check if that cell is alive. So if well, we don't have a function. So how do we know if that cell is alive or not? Let's write another function for that. So return a Boolean is alive, and we'll pass in our cell. So how do we determine if a cell is alive? Well, we can check our current state and determine if there's a tile there or not. So we could just say a return current state dot has tile at that position. However, this only works if we're not using a dead tile, which normally speaking, you shouldn't have a dead tile. Like normally speaking, a dead tile is just null, right? So if has tile, if it's null, well, then that returns false. However, if you do want to use a dead tile, this won't work. So instead, what we can do is say get tile. And if our tile is equal to the alive tile, well, then it's alive. That makes sense, right? We get the tile at that position. If the tiles are a live tile, well, that means that cell's alive. Okay, so here, if our if is alive, our neighbor, so if our neighbor is alive, then we increase our count. So this is counting how many neighbors are alive to some cell. Now, there's one flaw with this, which is that this loop will include the cell we're checking, which we don't want to do. So we might want to add in here, if x equals 0 and y equals 0, well, then our offset is 0, which just means it's the current cell. So we can just skip that one. So we can just continue here. If x equals 0 and y equals 0, it's just the current cell. So that's not a neighbor, that's itself. So we don't want to include that one. So we just skip by saying continue. Otherwise, if it actually is a neighbor cell, then we will count it. This is where technically using a for loop like this is not as optimized. Instead of just unrolling the loop, we could just unroll the loop and manually increase the count for each cell. Like we just manually check each of the positions. We can just entirely avoid this if statement altogether. But it is one extra if statement. It's not a big deal. That's like a micro optimization, so it doesn't really matter. So I'm just going to leave this because the code's a little bit simpler in a sense. It's really identical to this. Okay, so counting our neighbors, great. Check if this current cell is alive, great. So let's do that. So first, let's get the amount of neighbors. So count neighbors for that cell, and then let's determine if that cell is currently alive. Is alive. Okay, and then this is where our logic comes into play. If our cell is currently alive, or we'll say if it's currently not alive, and the neighbors equals 3, then it becomes alive. Okay, so it becomes alive. Else, if our cell is currently alive, and the neighbors is less than 3, or I'm sorry, less than 2, or greater than 3, then it becomes dead. So this means it's underpopulated or it's overpopulated. If it's underpopulated or overpopulated, it becomes dead. And if neither of those is the case, then it stays the same. That's the logic to game of life. So what happens when it becomes alive? Well, we don't want to update our current state. We want to update our next state. Because if we change our current state, it's then going to cause problems for the next cell that we're looping over. So we want to update our next state here. So next state, set tile at that cell position to be the alive tile. And if it becomes dead, well, then our next state, set tile, cell position becomes our dead tile. And then if it stays the same, well, we can just get the current tile from our current state and assign that. Cool. Now we do have this other hash set that keeps track of which cells are alive, because this is used to then figure out the initial set of cells to check. So we need to update that as well. So if a cell is becoming alive, then we need to add it to our set. And if it's becoming dead, then we need to remove it from our set. And if it's staying the same, then we don't need to do anything. Cool. I think that is it in terms of the actual logic. And I'll add some comments here to explain. So this is gathering the cells to check. And then this is transitioning cells to the next states. Okay, finally, we have these two tile maps. We need to swap them. So the current one becomes the next one, and then the next one becomes what was the old one. So let's store a reference to the old one is our current one. Then we'll update our current one to be the next state. So our current state becomes the next state. That makes sense. And then we can set our next state to be the old state. I'm just going to call this temp, actually. This is just what a temp swap looks like. This is very common in like in sorting algorithms for arrays, for example. You do swaps all the time, and this is what that looks like. You store one in a temporary variable, then you update that, and then you can go back and update the other one. Current state equals next state. Our next state becomes what that old state was. And at this point, our next state can just become cleared. We can clear it. That way, the next time we update our state, we're starting from a fresh place again. And that is it. Assuming we didn't make any mistake. That's all. So let's test it. Let's delete our notepad here. All right. All right, so we've got our initial pattern sets. Let's play this. And there it goes. And so this is our simulation. And so this is why I use this as our initial pattern, because this one's just really interesting. There's a lot going on. It's super dynamic. You've got some oscillators here. So there's a little plus signs that kind of oscillate back and forth. You also have these, which I refer to as gliders, I believe. Gliders or maybe bees. And those will just keep going on forever. And so this is where like the concept of an infinite grid is nice, because you want to just be able to see these go on forever. And if you use like a fixed size grid, then at some points you're only rendering tiles within that fixed grid, and then these disappear because, you know, it's only rendering the tiles in that space. So, yeah, so that's it. That's our game of life. Oh, and this is where also, you know, feel free to adjust the size to your preference. Right, so the larger we make this value, the more space we'll be able to see at once. It's kind of hard to find the right balance. In theory, you could actually change this programmatically, like based on, like dynamically change this based on the overall bounds of all the cells. But yeah, this is good. There's just a few more things I want to clean up in our code before we wrap up, as well as add a little bit of informational properties so we can determine what the current population is and what our iteration count is. So let me open up that script again. And actually, before I do that, I just want to show off one more time because we're not caching our yield statement for the interval, I can change this on the fly. Right, so it can be fast, and I can change it, let's say to update every 1 second. That's great. But I do want to clean that up and not produce garbage every single time. So I am gonna cache this. So we're just gonna store this in a wait for seconds here. Store this into a variable, and then we'll return that. That way I don't have to allocate that garbage every time. And also, one thing I should have been doing earlier is I should be yielding before we hit our while loop 1 time. And that's because we want to see our initial pattern, the initial state of our pattern before it updates. And so we won't want that initial pattern to last 1 cycle before it updates. So we should be yielding there anyways. Once again, I won't be able to change the interval dynamically, but I don't really need to anyways, so I don't mind caching this. Okay, the other thing I want to do is add some data or some informational properties to calculate the population and the amount of iterations and things like that. So let's add some read-only properties here. I'm going to call this population. It's going to become a public getter with a private setter. So effectively, it's kind of like a read-only property. Not exactly read-only, but similar idea. Do the same thing for our iterations here. And we'll do one for our time. Population, iterations, and time. Now, initially, when we set our pattern, we can set our population to be however many cells are alive. We should also update our clear function, which I just realized I never reset our hash sets, so I should do that too while we're here. Live cells that clear, cells to check clear, population 0, iterations 0, and time will be 0. And then after we update our state here, our population will just be whatever our new alive cells count is. Our iterations will always increment by 1, and our time will increment by the update interval. And so now, when we take a look at this, we can get some information. Now, to see those properties, we want to switch to debug mode. So we can go to this 3-dot menu and go to debug, and we can see those properties there. So here we can get the current population, the iteration number we're on, and then the overall time of execution. So that's it. That's all I wanted to do. Just to kind of clean up a few things and add those informational properties. Here I have my main project open, and I just want to showcase a few other patterns here. I've got like 100 different patterns set up already. So if you download the project from GitHub, it will include all of these, and you can take a look at them and play around with them. So to start, let's look at a few famous ones. For example, this queen bee shuttle. Let's drag that in. So this here is referred to as a queen. The thing in the middle is like a queen bee, but in this case, it's kind of going back and forth between these 2 points, which then ties into our next pattern, which is the Gosper glider gun, which I believe this pattern uses 2 queen bees that then generate gliders in between them. So that one's pretty cool. It'll just generate all these gliders over and over. And so that's like what a gun is. There's different categories of patterns, and guns are things where it'll generate an object and then shoots off. Let me just take a look at another one. For example, let's look at a buy gun. Yes, this one's pretty neat. You see, there it is. So it's producing these little gliders. That one's pretty cool. We also have these. I don't even know how to pronounce that, but these are ones that take a large amount of iterations to become stabilized. So these are like usually really complex ones. In fact, our pentonymal R is considered one of them. I don't really know which of these is good. We can just look at a normal queen bee. But yeah, these are patterns that will iterate hundreds, maybe thousands of times before they become stable. Yeah, this is a pretty cool one, actually. So that actually wasn't that many iterations. It was maybe 200 iterations, maybe a little less. But there are some of these that might take 1,000+ iterations before they stabilize. Some oscillators here. Let's see, which of these is interesting? A figure 8. Let's look at a figure 8. Yeah, so that's pretty neat. So it just oscillates back and forth. A lot of cool ones. That queen bee shuttle we looked at. So here's just, yeah, queen bee kind of goes back and forth between those 2 points. The puffer fish. So, or actually before we do a puffer, let me look at a spaceship. So let's look at like, let's look at this one. So these spaceships are things that'll kind of move on forever. So they like glide through the space. Like, so you have your basic glider, which is just like the small little one that you'll see these show up all over the place. But then you can have these more complex spaceships as well. So this one's pretty cool. And then we have things like puffers, which is similar to a spaceship, but it also leaves debris behind it as it moves. So this one's moving up and then it's leaving some debris in its space or in its place. Then there's a bunch of still lives. So these are like shapes that will come up where they become stable after 0 iterations or one, or I guess maybe you could say 1 iteration. But there's all kinds of shapes that might show up and they won't change. They've become 100% stabilized and nothing will update. So here's like a little Python. The boats, these different ships, boats and barges are pretty common. You'll see those show up a lot. So that's like a long boat, and there's a smaller version of that. Same thing with ships, but there's all kinds of stuff. Let's see what the snake looks like. Yeah. And so then you have the concept of wicks, which usually tie into still life. So let's look at a boat maker. So this is like a fuse or a wick that then produces boats. So I'll run that again. It's pretty quick. So you kind of got this fuse line, and then as it goes through, it generates some boats in this case. Same thing. That's like a beacon. A beacon, I think, is an oscillator, is it not? Yeah. So here's a beacon. Beacon oscillates between those 2 points. Yeah. So there's all kinds. A hive maker. This probably ties into the queen bee stuff. Oh, I guess it just creates the hives. Yeah. So anyways, there's all kinds of stuff in here. All of these patterns are available in my GitHub project. So feel free to download and play around, take a look at all those. There's even more, obviously, there's tons of them out there, but these are some pretty common ones. A lot of these are pretty famous. But obviously feel free to make your own patterns too. See if you can come up with a pattern that has some interesting life cycle to it. There's a lot of people that actually spend a lot of time trying to find patterns that have never been discovered before. So having some kind of tool program where you can quickly set some cells and then see what happens is pretty nice. But anyways, that's it. That's Game of Life. I really appreciate you watching this tutorial, and I hope you learned a thing or two along the way. Give the video a thumbs up or down to let me know how I did. Subscribe to the channel for more videos just like this one, and leave a comment recommending what you would like to see next. If you want to support my work even more, you can become a Patreon member to receive exclusive benefits, including early access to future tutorials and the Unity assets that I develop. Link in the description of the video. Thank you for watching. See you in the next one.